Okay, so we're going to go over the quiz number 7. Okay, can everyone see that?
Yes.
Okay.
Yes.
So pretty much the number one, just a basic so integrated circuit for an op amp. So the answer would be C for 2 input and 1 output. That is your basic op amp or the IC. So this is right here, the op amp. Okay, so you have is input, you got the inverter input and the non-inverting input, and you get only 1 output right here. So therefore the answer is C, as in cat, for number 1. Number 2, which of the following characteristic does not necessarily apply to an op amp? Okay, so the only one that does not apply is B, the low power. It does have high gain, high input impedance, and low output impedance. That is, so you have is this one right here. So your open loop, you're going to have infinite gain. So therefore you got infinite gain, and your input impedance, you're going to be infinite, and your output impedance is going to be approximately 0 ohms, or at the low amount. Okay, so that is the, so you're going to be, so low output impedance, high input impedance, and high gain. So that's applied to this one, ideal op amp. Okay, so the only one that does not apply is B, as in Bob, at the lower power for number 2. Now, number 3, the differential amplifier. Okay, so differential amplifier. So we look at the differential amplifier. So this is differential amplifier, would be this one right here. So it's part of the op amp. And so you have 2 input and 1 output. Okay, so so we got the, so that is this one here. So it is part of an op amp. It has let me see, it has 2 output. Okay, so it has 2 output according. Now it's a differential amplifier. So if you look at the single ended, yeah, you will have 2 output possible right here, output 1 and output 2. And this one, output 1, output 2 on a single ended on differential amplifier. Okay, so that's why the answer for number 3, it's also A and C. So the answer is D, as in David, for number 3. Okay, any question number 1, 2, or 3?
No.
Okay, next set. Okay, when an op amp is operating in single-ended mode. Okay, so single-ended mode. So you look at single-ended mode. So input applied to either positive or negative for the op amp, and the output and the other input is connected to ground, as you can see right here. So this is represent a single-ended. Either the signal is either put into the inverting side or non-inverting side, and the other one will be connected to ground. So the answer is B, as in Bob, for number 4. So one input is grounded and the signal is applied to the other. Okay. So number 5, in the differential mode. Okay, so differential mode is right here. 2 opposite polarity out of phase signals are applied to the input. As you can see right here, one is this one here, and the other one will be the opposite side. So that's why you got opposite signal. So opposite polarity signal applied to the inputs. So the answer is A, as in apple, for number 5. Okay, number 6, in the common mode. Okay, in the common mode, that means most of all the signals, both signals identical, is going to both input. Okay, so therefore the answer is the only one that apply would be C for number 6, and identical signal appears on both inputs. That is common. Okay. So any question number 4, 5, or 6? No. Okay. Next set. Okay, for number 7, the common mode gain is normally very, very low. Now you can look at the, let me see. So you can, for number 7, you can go see the e-handout 05 fall 2021 operation amplifier. It's on page 6, okay? And that answer is it should be very, very low, very low. Okay, so B as in Bob for number 7. Number 8, okay, so number 8, now this is CMR. Now CMR, you can calculate it just to getting the ordinary gain, which is would be 10,000. But if you want to calculate in dB, it will become to 80 dB. So therefore the answer is D as in David. For the answers B and C, okay. Number 9, with 0 volt on both input, an op-amp is ideally should have an output that equal to 0. Okay, so this is mainly we're talking about the ideal circuit, or you can look at this one right here. So it comes out to 0 volt. Well, your ideal here, we'll talk about the ideal one right here. As you can see, so you're going to be output here is going to come out 0 when you apply the same signal into the both input. Okay, so that was number 7, 8, 9. Okay, so that's C as in cat for number 9. So any question number 7, 8, or 9? Joe, do you have a question?
No, I don't.
Okay. Just checking. All right. So next set, number, okay. Now number 10, 11, and 12. Okay, 10 of the values listed, the most realistic value for open loop gain of an op-amp is remember, we're talking about when Mr. Pham was presenting, it's around 200,000. So the one that is closest to about 200,000 is D as in David for number 10. Okay, so that is the only one that's closest to the gain of the ideal one that we talked about in class. Okay. Number 11, a certain op-amp has a biased current of 50 microamps and 49.3 microamp. The input offset current is, so I offset equals I1 minus I2. Okay, so 50 microamps minus 49.3 microamps equals 0.7 microamps or 700 nanoamps. So the answer is A as in apple for number 11. Okay, the output of a particular op-amp increases 8 volt in 12 microsecond. The slew rate is, okay, so slew rate is the delta V out over delta T. Okay, so delta V out would be 8 volt divided by delta T, which is 12 microseconds. So you divide that, it yields 0.67 volt per microsecond. Okay, so the answer is B as in Bob for number 12. So any question number 10, 11, or 12? Okay, no question. Next set. Okay, so the purpose on offset null is to mainly just mainly to equalize the input that goes into now I don't have the exact circuit here, but mainly to equalize the input and also to make sure the output is 0 volt. So the output here should be 0 and the input here, so the input that goes into here to be matched with each other, so that way it's equalized. So the answer is D as in David for number 13. Okay, so we don't want any additional output potential, so we want 0 here, so therefore we need a 0, 0 in the input. Okay, number 14, for an op-amp when a negative feedback, the output is the feedback to, okay, so we look at for an op-amp with a negative feedback, the output is fed back to the inverting side. So right here, so according to this, okay, so according to this is what is get feedback. So whatever the output is, get some of it will feed back into the circuit, and it's going to the to the inverting side of your op-amp. Okay, so the answer is C as in cat for number 14. Okay. Number 15, the use of negative feedback, mainly to make sure that we can reduce the voltage gain because some of the voltage, output voltage is feedback into input, so therefore it reduces the gain. And also for mainly for linear operations. So the answer is A and C. So the answer is D as in David for number 15. Okay, any question number 13, 14, or 15?
Yeah, could you explain a little bit more the 13?
Number 13, the purpose of offset null. Okay, the offset null, you will experience this one in the lab where they're going to tell you to, you're going to turn, there's going to be a the pot where you can turn it to adjust so that way your input here would be, at the input here would be 0, 0. And so your output would be 0 out here, okay? So therefore we don't want any output that is, we just want the answer that is coming from directly from the input. But if you don't offset, you're going to have some voltage that exists here at the V out at the beginning. Okay. So in other words, just zero out the whole thing. Just make sure there's no voltage exists in here. Okay. So that's why we adjust it. So that way this side is 0, 0. And so the V out will be 0. So that just to make sure that there's no additional voltage that exists in the circuit. Okay. All right. Any other question? 13, 14, and 15. Okay, everyone's good. All right. So next thing is, let me see, scroll down just a bit. Okay. Number 16, the negative feedback. Okay, so negative feedback, we, like I said, it's going to be increases the input impedance and mainly that's what is mainly the feedback. So negative feedback decreases the gain, therefore the bandwidth would increase. So bandwidth increases, and therefore the input impedance would also increase. So the answer is B as in Bob for 16. Number 17, a certain non-inverting amplifier has a R input of 1 kilo ohm and feedback resistance of 100 kilo ohms. The closed loop gain is, so you have a closed loop and it's a non-inverting. So you put in the non-inverting. So closed loop gain is going to be 1 plus RF divided by RI. So you plug that into the equation. We know that RI is 1K and then RF is 100K. So therefore it's going to be 1 plus 100. You yield 101 as your gain. Okay, if the feedback resistance question 17 is open, the voltage gain is, it's going to be infinite because if you plug in the formula, so therefore 1 plus RF over RI is equal to 1 plus, remember the feedback is going to be open, so therefore it's going to be infinite resistant. So any infinite resistance divided by 1 kilo ohm, that will be infinite, plus 1 will be infinite plus 1. So therefore you're going to get infinite output. Okay, so bandwidth with it, therefore so you're going to be having mainly the voltage would increase. So the answer is A as in apple for number 18. So any question on 16, 17, or 18?
Okay.
Okay, no question. Okay, so that's pretty much it. Okay, back to you, Mr. Pham. Thank you.
Okay, thank you, Sam.
Yes, sir.
So you guys can see Sam now know a lot compared to the first time we get through the program. The thing we have to review the quiz. So in order to understand it, you guys have to go through the lecture, okay? Try to read it, the handout, over and over. The quiz basically we concentrate on understanding. Very less calculation. Okay? The thing is, normally, just a very basic calculation you must know, but we not go into too much in the calculation. Okay? So make sure you try to keep the quiz in order later on. When you get the job interview, that is the one you look over just for the review. Okay, any question? If it's not, make sure everyone not reading the display before we start the program. I'm telling you, okay? Next week we get only 1 day meeting with me. And Tuesday and Wednesday will be in class level. And we will be start the holiday from December 16 and will be returned to the class on December 3rd. And at this time, I have to go to some subject for the lecture in order to try to get it done before end of the first week of the January. Okay? So again, if you get any question, any problem with any circuitry in the level, just text to me. And I will be in Zoom with you, try to help you out if I can. Okay, any question? If it's not, then I will be changing to my iPad.
Hey, Mr. Pham, just real quick. So Thursday of next week, there's no class, only Monday, Tuesday, Wednesday.
Exactly.
Okay, thank you.
Okay. We continue with the ActiveFilter. Okay. So what you need to know is basically the definition for the filter. Okay. Let's see. Filter are circuit that are capable of passing signal with a certain selected frequency while rejecting signal with the other. So you can see you get a radio. You can tune to the different channel. That means each one they get a different frequency. Okay. That's what they need the filter. Okay. And also they say this property is called a selectivity. When you tune the radio, you select a certain frequency. Okay. Active filter is transistor or op amp. combined with passing RCRL or RCL circuitry. The reason we get two filters type, one passive and another active. Passive filter or active filter working identical, same thing. Only thing is, passive they just using RCL. RCL don't need any power. That's what they call a passive. However, if you're using the transistor or using the op-amp, you need the power supply. That's what they call active. Okay? And they said that the active device provide voltage gain. You already know. You're working with the op-amp and you get the gain. However, the passive circuit, that means RC, RL, RCL, that passive, that given you the frequency selectivity. That means whatever frequency that's coming out from RL, RC, RCL. And the passive circuit provide frequency selectivity. So that's why when you tune in your radio, you change the value of RCL, okay? To select a different frequency, different channel. And we get the four basic of the filter. Not much, okay? First is low pass filter, high pass filter, band pass filter, and a band stop filter. Okay, now, first thing we're talking about low pass filter. Okay, normally when you interview, they given you this picture here. And the question is, they can ask you, what is it? So, who can answer that? If you're looking into that picture here, and they're asking you, what is it? Then what happened? How can answer? How can we answer for that question? Who can tell me?
Can you ask the question? Can you say the question one more time?
The question I given to you, this picture here. I can ask you, tell me what is it?
It's a low pass filter.
It's a practical low pass filter.
Yeah, it's the ideal.
Not ideal, non-ideal.
Ideal here.
Oh, yeah, I'm sorry. Yeah, that's the ideal is the one on the left and the one on the right is practical. It's, in other words, practical means, well, first of all, ideal is how something should work theoretically. But from But from a theoretical standpoint, that's not how these filters work.
Yeah, they don't have any dB.
Right.
These are practical. That means they could be dropped
3 dB.
right at the critical point, at the cutoff. However, the answer is not complete yet.
It's the frequency response curve.
Now that is too general. The thing is you can get low pass, high pass, band stop filter. And they want to know this picture here is what? Okay, now the answer will be, this is the output of the low pass filter. See that? This have to be an output or response. of the all-pass filter. Okay. So basically, when you're looking into the low-pass filter here, okay, this what we call a mid-range. What that mean? That mean any point here on this frequency, V in and V out will be the same. If you get 10 volt coming in, you get 10 volt coming out. No loss. Okay. However, at this point, FC means cutoff frequency, critical frequency. Okay. That means they get a different name if you're looking into the handout. At cutoff frequency, then the output will be going down 3 dB. If you get the input at 10 volt, at this point, to calculate what is the output voltage, then you cannot using minus 3 dB. You have to understand a equivalent to minus 3 dB is 0.707. Then you take 10 volt times 0.707. That means the output at the cutoff here will be 7.07 volt. Okay. And also they said slope minus 20 dB per decade. What that mean? That means if you increase the frequency cutoff to 10 times, I given you the example, you get the FC is 1 kilohertz. 10 times FC means 10 kilohertz. So at 10 kilohertz, the output will be going down 20 dB. If you want to calculate output at 20 kilohertz, okay, I mean FC equal 1K. 1 decade means 10 times 1K, 10 kilohertz. And they down minus 20 dB. So you do not do anything with minus 20 dB to calculate. Then you have to see what equivalent for minus 20 dB. Okay? And a minus 20 dB equivalent to 0.1. Okay? You get input 10 volt. And now they're going down 20 dB. So 10 volt times 0.1. Okay? You get 1 volt. Okay? That is basically you must understand for on up the filter will be the same way. If you understand one, no problem to the other. Okay, if you get any questions, just go ahead, okay? Let me know. I want to make it clear for everyone. Okay, let's see what else. One pole, low pass filter. Okay, one pole, that means in that circuitry, you get only one resistor and one capacitor. You understand they already telling you. Resistor or capacitor, that will be passive component try to changing the frequency. Okay, so low pass filter, they only one resistor and one capacitor. By the way, 2 poles, then you get 2 resistors and 2 capacitors. Okay, and 3 poles, you get 3 resistor and 3 capacitor and so on. By looking into the circuitry, you're able to recognize is it a 1 pole low pass filter or 2 pole low pass filter or 3 pole. Okay, low pass filter only allow low frequency signal from 0 Hz to the cutoff frequency. Now, we're going back on that one here. If you want to do in calculation the bandwidth of the low pass filter will be going from 0 Hz up to the cutoff. After the cutoff, we don't care anymore. Okay, so the signal will be only allowed to going from the 0 Hz up to the cutoff frequency. That's what we're talking about, the bandwidth. Okay. Okay, so they say only allow low frequency signal 0 Hz to its cutoff frequency, FC. Okay, to pass why they blocking not any higher frequency. So basically they calculation up to the cutoff only. Cutoff frequency or corner frequency or critical frequency, okay, or break frequency is calculated by the formula FC equal 1 over 2 pi times RC. In this formula, FC will be in Hertz, R will be in ohm, and C will be in farad, and you know what pi equal, right? 3.142. At the cutoff frequency, the gain is down 3 dB, or the output going down to 70.7%. That's the same 0.707 of its maximum values. After cutoff frequency FC, output decrease at a constant rate at the frequency increase. That is when the frequency increased tenfold, 1 decade. The voltage gain is divided by 10. In other words, the gain decreased 20 dB each time the frequency increased by 10. 1 pole LPF, 1R, 1C, roll-off rate is 20 dB per decade. 2 pole, 2R, 2C, roll-off rate might be 40 dB. And 3 pole, 3R, 3C, roll-off rate minus 60 dB. And you understand, you want the roll-off rate have to be higher, bigger number. Okay, that means they want to stop quickly after the cutoff frequency. Okay, so for minus 20 dB, then you can get more noise. Okay, that means at the cutoff, you still allow the signal to go. So that's why in practical, they not using minus 20 dB. That apply for the class, for the school only. Okay, like your cell phone, you get the filter, and that filter have to be run off with a very, very big number. So that's why no noise. Okay, let's see comparison. ID low pass filter with actual filter. So basically, this is the ideal. Okay, that means at the cutoff, they going down quickly. Okay, this is a bandpass, and this is a bandwidth. However, this is, they say, compare ideal low pass filter, okay, with the actual filter. So basically, that will be, you get a cutoff right here, okay? So that will be practical filter. Ideal, they will be cut off at this point, okay? And that telling you you get the bandwidth from 0 to FC, cutoff frequency. And this will be show you a different low pass filter, 1-pole, 2-pole, and 3-pole. So for the 1-pole, you can get down 20 dB per decade. Okay. However, this is basically ideal. That's what they wanted. So any filter go close to the ideal will be much better. So when you get a 2-pole, they much better than 1-pole. And this will be 3-pole. They close to the ideal. What happened? They want after cut off, they don't want any more voltage. Okay, that's causing the noisy. Okay, so the same filter, the same cell phone, some very cheaper, but some cost a lot money. The thing is they get a very, very good filter. Okay, any question up to this point? Okay, if it's not, let's see. That will be show you, okay, in detail for 1-pole, 2-pole, 3-pole. Okay, now example. For the LPF low pass filter circuit show, that means resistor right here. 1 kilo ohm, C, 0.1 microfarad, input 10 volt RMS. Okay, that means voltage apply is 10 volt. So the first thing, they want to know, calculate the gain of the filter. They're using the op-amp, and they can using inverting amplifier, non-inverting amplifier, or they can using the follower unity gain amplifier. So when you're looking into the circuitry, you must recognize which configuration of the op-amp in order to calculate the gain. Okay, so on this circuitry, when you're looking into that, okay, that will be follower, unity gain amplifier. If you don't know, you have to go back into the operation amplifier, okay, to read it regarding the part of the follower, okay? The follower or the unity gain, then the gain equal to 1. Whatever input coming in and will be the same exactly at the output. So calculate the gain and you say the gain equal 1. Okay. The gain will be not no unit. Okay, any question on the gain? The thing in the quiz, sometimes we can using non-inverting amplifier, try to get more gain. Okay, in this example, in and out the same, the gain equal 1. Then you have to using follower. Okay, number 2, they want the cutoff frequency. In order cutoff frequency, you have to using the formula. FC equal 1 over 2 pi RC. That's what given you 1.59 kilohertz. And they want to calculate the V out at the cutoff frequency. Okay, V in is 10 volt IMF. At the cutoff, they going down 3 dB, equivalent to 0.707. You take 10 volt times 0.707. You get at the cutoff frequency output will be 7.07 volt. Okay, up to number 3. Any question? Okay, if it's not, number 4. They want the output at 10 times of the cutoff frequency. Who calculate to telling me what you get? Number 4. Okay, so basically 10 times FC. Okay, that means they will be down. Minus
It's 1 volt.
20 dB. Okay, that equivalent to 0.1. And now you want to calculate the V out equal 10 volt RMS times 0.1. You get 1 volt IMS. Okay, you must understand, must know how to calculate the basic thing. Okay. That's why I given your guy quiz. When you're looking into the question, you can know right away what to do, how to get it done. That's just a very, very basic. Normally, you don't care much about the circuitry. The circuitry very, very complicated. However, when you do testing, they already telling you what type of the filter. Two-pole low-pass filter or two-pole band-pass filter. They're telling you everything. Cannot remember the circuit. However, you have to understand that basically for a low-pass filter, two poles, how they work it in order to calculate the output. Okay, so any question for this example? Okay, let's see. Now, for LPF circuit, that means this circuitry here. Okay. The input voltage is 2.5 volt IMF. They want to know what is the gain for this circuitry. Okay, so go ahead and calculate. Who get the answer, let me know. This is the non-inverting. Okay. And they already given to you. The gain equal 1 plus R2 over R1. Okay, this is R2. This is R1. Okay, 9K divide 1K. Okay, you get 10K.
Mr. Pham, I have a question.
Go ahead.
So you know how the R2 is right here? What does 9K1 mean?
Oh, that's a typo.
Oh, okay, thanks.
Thank you. Okay. 9K divide 1K, you get 9. 9 plus 1, you get 10. So the answer here will be 10. Okay, thank you for correction.
You're welcome.
Okay, now they want to know cutoff frequency. Okay, again, cutoff frequency FC. One over 2 pi RC. Okay, R10K, see 100 nanofarad substitute and calculate telling me what you get. I don't know the answer, so I need the answer. So later on for the other student, they do it the calculation, they get a correct answer. So what the cutoff frequency equal? What nanofarad equal? Is it 10 minus 9 or minus 12?
I think the answer is 159 hertz.
Okay, 159. Hertz.
Hertz. The resistor is 10 times bigger than it was in the last problem. And the capacitor is the same.
Okay. That makes sure, you know, when they have to do calculation, they get the right answer. That's a minimum calculation technician have to do. We don't try to need you guys to solving the equation. No. If you get into the college, they will be just talking about theory. So that's why they go more detail in everything need the calculation. Like you learning, for example, for DC circuitry, and they have to using KCL, KVL input loop to solving the equation to get the value. But the thing is, right, at this time, if you want any value, you can using the simulation. Either M5, MSIM7 or P5, you can get any value you wanted. You want the training for the technician. We have to deal with the more what the job technician have to do. If you go engineering, okay, you can go more detail. But the AS degree in the community college, they still going not a quite good direction. That's what I talking to the professor at the community college when they asked me about this program. Okay, number 3, VL max. So let's see, VL max, that means you take the gain time VE. So look like 25, right? For my understand, look like 25. Okay. That means you take the gain time, the input, and the number 4, they want the output at the cutoff. You take 25 times 0.77.
17.675.
17.675. Perfect. And now at the cutoff, at the 10 time frequency of the cutoff, they will be down 20 dB.
2.5.
That means to take that 25 times 0.1, 2.5, right?
Correct.
Okay, any question on this example? However, The same problem. If we're using two-pole low-pass filter, the calculation should be different.
Mr. Pham,
Yeah,
just want to double check on FC. Is that 159 kilohertz or hertz? Can,
you
some,
mean,
can some of the other students verify that?
okay, you mean on the cutoff you get
159 kilohertz.
159 kilohertz. Who else get the difference? Someone told me 159 hertz. And now you say 159 kilohertz. Okay. The calculation will be easy if you know nanofarad equivalent to farad will be 10 power what? -9 or -12?
Is it -12?
-9.
-9.
Ah, okay. All right.
Nine.
That's my mistake. Okay, thank you.
Welcome.
Pico's 12.
Right, pico -12. Okay, again, any question on this problem from number 1, 2, 3, 4, 5? Any question you confusing or do not really understand?
Teacher, point number 5. Could you explain a little bit?
Okay, number 5, they say at the 10 time cut off, they going down -20 dB. And you cannot do anything with a -20 dB. You have to deal with a number that's equivalent to 0.1. Okay, so basically at the output, you can take 22.5 volt input, and now you will be time to 0.1. 0.1 equivalent to -20 dB. Okay. 2.1, I mean 2.5 times 0.1. The answer have to be 0.25, not 2.5. Okay.
Do you multiply that by Vn or do you multiply that against V out max?
Oh, sorry.
Yeah, the gain is 10. So
Yeah,
it should
yeah.
be 10 times.
Thank you. We have to multiply by V out maximum. V out maximum is 25, right? Okay, so you get 2.5.
Looks good.
Yeah, thank you.
Thank you.
Okay. High pass filter. path and a frequency higher than the cutoff frequency, FC. Okay. Cutoff frequency formula, same thing, 1/2 pi FC. Okay, so you understand low path, then that will be no problem. For the high path, only thing if you're looking into the circuitry, they're changing the position of the capacitor and resistor. Okay, that for low path resistor here, capacitor in here, high path now they change. Capacitor will be in this position in R. Okay, and if you're looking into the output of the low high pass filter, okay, so basically this is the mid range. Input output will be the same. When you go in the cutoff frequency here, okay, and they will be down 3 dB, and the same thing like low pass filter, and the bandwidth or path band start from cutoff to infinity here. Okay. Any signal less than cutoff will be try to reduce it. Okay. And now they're giving you the example. For high pass filter, so input is 2 volt IMS, R9 110 ohm, C01 microfarad. They want to know the gain. And this is the unity gain. So you know the gain equal 1. Okay. And the cutoff frequency, you do that calculation, telling me what you get.
One 1.75 kilohertz.
You say 75?
1.75 kilohertz.
Okay. You say 1.75. Kilohertz, right? You get anyone get the same answer. Make sure you have to exercise, okay? That means you have to do the calculation. What Sam you get?
I got exactly like David, 1.75 kilohertz.
Okay.
Yeah, me too.
Okay, number 3. V out at cutoff. That means V in a 2 volt. So V out at the cutoff, you take 2 volt times 0.707.
It's 1.414 volts.
Okay, 1.414, correct. Okay, and at the 10 time,
0.2 volts.
you take 2 volt times 0.1, right?
Correct.
Okay. 2 point times 0.1, that means 0.2, right?
Correct.
Any question about it? Example. Okay. Now they're using non-inverting. And basically, I not go to the example. You have to do your calculation. Okay. And that maybe will be in the quiz for you to do. Now, you can see this is the circuitry for tuple. If you're looking at, we already tuple, that means two capacitor, two resistor. And you looking here, you can see C1, C2. And resistor will be R3, R4. Okay. What the op-amp configuration they built for this filter? What's the name of this op-amp? What is the name?
Non-inverting.
Non-inverting?
Exactly.
Non-inverting.
Non-inverting. The reason I asked the question is, they said in the two pole, you get two capacitor, two resistor. That's why two capacitor easy to recognize. However, two resistor, you don't know which one. You can get a R1, R2, let's see, 1, 2, 3, 4 resistor. If you don't know the configuration for the op-amp, then you can mix up on the resistor. Okay, so R1, R2 using for the gain of the amplifier, and the leftover will be R3, R4. That will be two resistors for the filter.
Mr. Fan,
And then, yeah,
my question is, since you have one resistor, one capacitor, one pole, two resistor, two capacitor, two pole, does R3 go with C1 and R4 go with C2? Or
yeah,
is it just the opposite?
right.
Right, what do you mean? Which goes with
That
which?
means you can using, they don't care which one go with what. You can see the formula.
Mhm.
They want to cut off, you say they get a 1/2 pi times R3, R4, C1, C2.
Mhm.
Doesn't matter R1 go with C1 or R2 go with C2. That don't make any difference.
Okay. And
Okay.
also to the right in that box, you had the gain, which is 1 plus R2 over R1. So that's for the non-inverting, correct?
Correct.
And that's right how you do the cutoff. It's R3, R4
R3, R4.
times,
C1.
yeah, for the cutoff. Okay. Thank you.
Yeah, the thing is when you calculate the cutoff frequency, you have to know what resistor belong into frequency. Okay. That's what I try to asking you. If you know this is a non-inverting, and you have to know what is the gate, R1, R2 will be make up the gate. The leftover will be R3, R4. Therefore, a passive component, okay? Try to calculate the frequency. Okay, let's see quickly. Now, we try to finish it today. And tomorrow we'll be talking about comparator. And if we get a time, we'll be talking about the last one. That will be JFET transistor. Okay, we'll be upload the JFET tomorrow. Okay, band pass filter. Okay, so if you're looking into the circuitry, they get R1C1. Okay, and basically they combine a high pass filter with the low pass filter to make the band pass. Okay, if you're looking into the circuitry here, this is the high pass. Pass any frequency higher than cutoff. And this is the low pass. Will be pass only frequency less than the cutoff. So this one they show you how they working. For the signal for the output here, high pass, any signal higher than cutoff, they allow to pass. When they hit into the low pass filter, and they will be stop any signal higher than the cutoff. So that's why they come up with the output of the band pass filter. Okay, so the band pass filter will be make it up by the high pass and the low pass filter. That is a more detail. However, they asking you what is it here. The answer will be that will be the output of the band pass filter. Any signal higher than F low allowed to pass. Any signal less than F high allowed to pass. Okay, outside frequency will be cut off. Okay, let's see. Here, more detail here. Okay, so this is again, this is the output of the band pass filter. Okay, you get F low and you get F high, upper and lower cutoff frequency. Okay, the bandwidth, that means this is the bandwidth. You want to calculate, you take F high minus F low. That's what you get the bandwidth. Okay. And if they want the quality Q, okay, that will be equal F center divided to the bandwidth. F center equals square root of F1 times F2. Okay, that means F1, F2. Quality Q control the roll of rate and the bandwidth of the filter. Okay. So I'm looking into that thing here. I know this is a stop band. Also, this is a stop band. Top band will be from here to here. Okay. So for the band pass filter, you can get that you cut off frequency, one F1 and the other F2, or F low or F high. And in the middle here, you get the frequency, they call it center frequency. Okay, let's see. This is the inverting band pass filter. That means they're using the inverting, okay, amplifier. Okay, and the voltage gain will be minus R2 divided to R1. Okay, and cutoff frequency FC1 and FC2. Basically, I never remember the circuitry for the band pass filter. This is a simple thing to show you. However, in the real world, at work, they get too many things. Okay? Only thing is they will be telling you this is the band pass filter. And they telling you also the gain if they have it. Okay? And the cutoff frequency for low cutoff and the high cutoff formula. However, you don't care much about the formula. You just the technician try to test. They telling you lower cutoff, 3K, or higher cutoff, 6K, for example. When you testing, you measure, you get the value. Okay? Right or wrong. But you never have to do any calculation. If you want more detail, go university. They will be given to you more. The thing is, engineer, they have to design the filter. Then you have to go into the detail. We just a testing. We not design anything. Just they telling you what to test, and you follow that and do the job. And last one, band stop or notch filter. That's opposite to the band pass filter. Okay? That means any signal higher than F high or lower than F low, they allow to pass. Any signal between F low and F high, they want to stop. Okay? This is a different, just opposite to the band pass filter. Okay, let's see. This one they show you the different output of the filter. 1 pole, 2 pole, 3 pole, 4 pole. Okay. So basically, the best you want will be 4. Okay. Region A, they get a narrow band. Okay. So will be less noise. When this one here, okay, you must get more noise. Okay. So they say how cascading filter section narrow the bandwidth and improve selectivity. Okay. So that's why in the past, maybe 20 years ago, 10 years ago, when you tune in your radio, you can hear the noise going from one channel to the other channel. Okay. However, the radio now, when you're moving, you didn't hear anything. That means they get a very, very good filter. Okay. And this one again, they just try to show you output filter, okay, for different name. Like you get a elliptical, a chapter, a butterworth, a best cell. If you're looking into this output filter here, make sure you understand. This is the mid-range right here. Okay, and this basically the noise dribble. Okay, that's just the noise. So the question is, if you're looking into the different filter here, which one will be much better? And now you can telling me which one.
The Bessel is the best one, isn't it?
Which one?
The Bessel. Right there.
Bessel.
Yeah, right there.
Right. Vessel, they get a very good for the cutoff. However, you're looking at into the mid-range, they don't have any ripple. Okay?
But we don't want any ripple there.
Exactly. You don't want any ripple. Get the noise.
So,
Jeopardy.
so of all 4 of those filters, the Bessel is the one that's, I can't say it right, but more correct how we want it.
Right. Now you see Jeopardy. This guy. They get a better cutoff than the Bessel. However, they get the ripple. You don't want the ripple. You don't want the noise. Okay? And also elliptical. They get a better cutoff than the Bessel. However, they get a big noise. Okay? Better worse. But the worse. They don't have a noise. However, the cutoff is too bad. Okay? Far away. We don't want that. So the answer for selection here will be Bessel.
Hey, Mr. Pham, also on these, when you looking at these things for the color, you looking at the roll-off rate?
You care about roll-off rate.
I'm saying, is that what you're looking at?
Right. You're looking into make sure they don't have any noise. Priority. And the next will be cut off.
And the high roll-off rate is better than the low roll-off rate.
Exactly.
Okay, thank you.
But on this one, they don't care about the high or low roll-off rate, but they care about if you're looking into this output here, which is the best selection, that's what in the view, they just given to you that picture. And they can asking you, which filter you think is the best selection? Especially for any student want to apply into the defense company in San Diego. The thing is, defense company, they working with the communication, and filter will be in communication. Okay, any question up to this point? Okay, so this just a more detail, okay, for you to looking into it, okay? And it also active high path, and you can read it. We don't have to go. Now, only thing, I just want to talking about this part here. When I'm looking into the output here, I know this is the output of the bandpass filter, okay? And this is the circuitry for bandpass filter, okay? So, bandpass filter pass on frequency bounded by FC2 minus FC1, okay? So this is the bandwidth from here to here, okay? And lower frequency limit and upper frequency limit, that's what you calculate the center, okay? Right here, this is F center. Calculate by F square root FC1 times FC2. And also, okay, they talking about Q, okay, quality equal F0 divided to bandwidth. How good that filter supposed to be. Okay, the note here, Q greater than 10, they will be a narrow band. However, after calculate Q, if they less than 10, that will be a wide band. You want the narrow band, you don't want the wide. And this is the circuitry in the textbook telling you band stop filter, okay? And this is the band stop filter here. This is the frequency higher than, lower than the path, and the frequency between cut off. They want to reject. Okay, nothing to go with the that thing. Okay, any more question, anything else? So tomorrow we will be talking about comparator. If you not download it, make sure go to the website and download for comparator. And make sure you download the quiz number 8. We will do it tomorrow. Okay, any question, anything else, I can answer you.
Wait, so where's the comparator on? So the comparator, what is that? Do I go to handouts?
In the handout.
Yes, and which one does it say comparator?
It's comparator.
Yeah, where does it say that? And do you mind if I switch screens? If I share screens?
Okay, so I have to stop there on my iPad.
It's on 1025. It's E handout number 7 for fall.
So where's comparator?
It says E handout 07 fall 2021 comparator.
Wait, hold on.
Posted on 1025.
Oh, I think I see it now. 10/25/2021, right?
Correct.
Correct.
Oh, good. Thank you.
That we will be talking about tomorrow.
Okay, thank you. Bye.
Okay, the thing is I could not, I know I already uploaded, I couldn't remember in detail. Okay, sorry. So now you know that, okay. But make sure, you know, on up the handout. Please try to take the time to go over and over. Up to the point you don't have to remember. They're already in your memory. Like myself, I see the circuitry, I know, okay, this is inverting amplifier or non-inverting or follower or summing amplifier. Okay, that will be good for you to do the job. But really, in the company, your job will be test the circuit. An engineer already telling you everything. Is it band pass filter or low pass filter or whatever? They just telling you how apply the input and measure the output like you're doing in the left volt. If you measure the output as they want it, that means they pass. Otherwise, that will get a problem. And your job will be fix it. Okay? That's a very, very simple thing. You don't have to go too much detail, anything. Everything engineer already showed you in like my handout. Okay? What apply and they measure output, what they wanted. Exactly same when you do left volt, when you build the circuitry. However, in the company, you don't have to build it. They already build it. Just apply input and measure the output. If that correct output, that means pass. Otherwise, you fix it. You make it work. Okay, any question? If not, okay, good night, everyone.
Good night, everybody.
All right, have a good night.
Good night.
Good night.
All right.